Hi guys, myself Rutu Dakhore and I'm going to present a project on bike sharing demand prediction. First, let's go over the project summary. This project aims to develop a machine learning regression model to predict the final demand for bikes. Historical data on the bike rental and environmental factor will be utilized to create a model that optimizes inventory management and enhance customer satisfaction. By accurately predicting bike demand, this ML regression project aims to support bike rental companies in optimizing inventory management, reducing costs, and delivering better customer service. The insight gained from the project will enable data-driven decisions such as adjusting rental prices, resource allocation, and improving overall operational efficiency. So, this is the GitHub link for my project. Project problem statement. At present, numerous urban cities have implemented rental bikes as mean to improve mobility convenience. Ensuring the availability and the accessibility of rental bikes to the public in timely manner is crucial as it reduces waiting time. Consequently, the challenge lies in establishing a reliable and consistent supply of rental bikes. The key aspect involves accurately predicting the number of bikes needed during each hour to maintain a stable provision of rental bikes. The data description we have provided with different attributes such as date in year, month, and day, rented bike count, hour, that means the hour of the day, temperature, city, humidity, wind speed, visibility, dew point temperature, solar radiation, rainfall, snowfall, seasons, holiday, and functional day. So let us start with importing important libraries. First, we will import pandas, numpy, matplotlib, and seaborn. Then we will mount the drive and give a file path for our dataset, and we will give a name like a bike data frame to this. So let us start with data exploration, data cleaning. First, we will check the first five rows and the last five rows. We will check total rows and columns in dataset. Then we will check the info of dataset. Here we have null values and missing values 0. Date columns need to convert into proper date time. Columns to convert into numeric for modeling purposes, and rename columns. First, we will move to check columns. Then we will convert this date into date time, and we will check. As you can see, the date time has been changed here. Now we can drop a day and date column. We will get holidays. After that, we will check the summary to check the mean max. We will check for null values. We have 0 null values, and we will visualize null values using heat map. Here we have got no heat because there are no null values. So we have completed our data exploration. Now we will move over to ED. First, we will create a numeric column list and create a categorical column list. I mean, using a block spot, we will visualize. Then we will add two more categorical columns, that is month and weekdays or weekend. Here from above bar chart, we have got some observation. Summer season had the highest bike rent counts. People are more likely to rent bikes in summer. Bike rentals in winter is very less compared to other seasons. Now, high number of bikes were rented on no holidays. On no functioning day, no bikes were rented. We have only 295 counts of no, thus we can drop the 295 values. Most of the bikes were rented on weekdays compared to weekends. From March, bike rent count started increasing and it was highest in June. So we will check the bike rent count trend with respect to hour on functioning day, weekends, weekdays, season, holidays, column. First, we will bike rental trends with respect to hour on holiday or no holiday. Here, observation. There is sudden peak between 6 or 7 a.m. to 10 a.m. That is office time, college and going time would be the reason for the sudden peak. Again, there is peak between 10 a.m. to 7 p.m. Maybe it office living time for above people. Then we will check the rental trend with respect to hour on functioning day. Here, observation. Here the trend for functioning day is same as no holidays. Only the difference is on no functioning day, there is no bike rental. So we can drop the no functioning day column row. Bike rent count runs with respect to hours on seasons. Here we can see the season. Blue is for winter, green is for spring, red is for summer and autumn. Then we will check in respect to with hours on months. Similarly, we will check bike rent count trends with respect to hours on weekdays and weekends. So let's check the distribution of target variable, that is bike rented count. Thus, we have normalized or dependent variable squaring root method. So let's check the distribution of independent variable here. Let's check the relationship between dependent variable, that is rented bike count and remaining columns. So here is the summary. In R, there is sudden peak between 6 to 7 a.m. to 10 a.m. office time and college. Second, again there is peak between 10 a.m. to 7 p.m. office living time. And we can say that from morning 7 a.m. to evening 7 p.m. we have good bike rent count. Temperature. For decreasing temperature below 0 degrees Celsius, the bike rent count is significantly decreased because maybe people don't want to ride bike in such cold temperature. But for normal temperature, the bike rent count is very high. Humidity. Here it seems like humidity is inversely proportional to bike rent count. As humidity percentage is increasing, there is decreasing bike rent count. Wind speed. Up to wind speed 4 ms, there is good bike rent count. Visibility. It is very obvious that as visibility increases, the bike rent count also increases. Dew point temperature. It again the same as temperature. As dew temperature goes below 0 degrees Celsius, there is less bike rent count. Solar radiation. Here the amount of rented bike is huge when there is solar radiation. Rainfall and snowfall. It is very obvious that people usually do not like ride bikes in snow, rain and snowfall. We will check the correlation between dependent and independent variable. Here we can see temperature and dew point temperature are highly correlated. So let us move toward the modeling. Let's prepare our data for modeling. Here we will be modeling our data set to get to linear regression. So here we have final info before going for modeling. So here is the final info before starting our linear regression. So what is linear regression? Linear regression is a statistical modeling technique used to establish a linear relationship between dependent variable and one or more independent variable. It assumes that the relation between variable can be represented by a straight line. In linear regression, the dependent variable is the variable that is being predicted or estimated, while the independent variable, also known as predictor variable or features, are variable used to predict or explain the behavior of dependent variable. The goal is to find the best fitting line that minimizes the difference between observed value of dependent variable and predictive value of the model. Here we will start our linear regression. And we have created the training result data frame. So we will evaluate the test data set. Here we can see a graph for a predicted and actual versus actual. So after this linear regression, there are three types of linear regression: lasso, region, elastic. We will go into one by one. Lasso, that is L1 regulation. It also stands for least absolute shrinkage and selection operator. It adds a penalty term equal to the absolute value of coefficient sum to least the square objective function. The penalty encourages the model to shrink less impact coefficient to 0, effectively performing feature selection. So we will start with lasso. Here we will do an evaluation on trend data and evaluation of test data. After completing this, we will move to ridge, that's L2 regulation. What is L2 regulation? Ridge regression adds a penalty term equal to the squared sum of coefficient to the least square objective function. This penalty term encourages the model to shrink the coefficient towards zero without eliminating any of them entirely. Rich regression is particularly effective when dealing with multicollinearity when there are strong correlations between the predictor variable. We will start with our L2 regularization. Here we will start with evaluation on trained data, then evaluation on test data. We will do a greed search on ridge. Then after completing this L2 regression and L1 regression, we will move to elastic net. What is elastic net? Elastic net combines the L1 and L2 regularization technique. It adds both the absolute value of coefficient sum and the squared sum of the coefficient to the least square objective function. The elastic net penalty allows for the balance between the benefits of L1 and L2 regularization. It can handle multicollinearity, perform feature selection, and provide more stable and reliable result compared to using lasso or ridge alone. We'll start with our evaluation and test data set. We will start with evaluation on training data set and then move to evaluation of test data set. After that, we will move to the algorithms, that is decision tree regressor with normal and hyperparameter tuning, random forest regressor, grid search CV on random forest, gradient boosting regressor, and grid search CV on gradient boosting regressor. First, decision tree. We will start decision tree with evaluation on training data set and then evaluation on test data set. We will look at the conclusion later. Then with hyperparameter tuning, random forest regression on training data set and on test data set. Grid search CV on random forest, same training data set, then test data set. Then gradient boosting regressor, evaluation on training data set, and then evaluation of test data set. We will then perform grid search CV on gradient boosting regression. Evaluation on test data set and evaluation on training data set. So, in conclusion, as we have calculated MAE, MSE, and RMSE and R2 score for each model, based on R2 score will decide our model performance. Our assumption, if the difference of R2 score between trained data and test data is more than 5%, we will consider it overfitting. Linear, lasso reach, and elastic net. Based on provided data frame, it is evident that the linear, lasso, reach, and elastic regression model exhibit nearly identical R2 score, that is 61%, on both training and test data. This result remained constant even after implementing grid search CV from model tuning. Decision tree regressor. On decision tree regressor model without hyperparameter tuning, we got R2 score as 100% on training data, and on test data it was very less. Thus our model memorized the data, so it was overfitted model. After hyperparameter tuning, we got R2 score as 88 on training data and 83 on test data, which is quite good. Random forest. On random forest regressor model without hyperparameter tuning, we got R2 score as 98 on training data and 90 on test data. Thus our model memorized the data as it was overfitted model as per our assumption. After hyperparameter tuning, we got R2 score as 90% on training data and 87 on test data. Gradient boosting regression. On random forest regressor model without hyperparameter tuning, we got R2 score as 86% on training data and 85 on test data. Our model performed well without hyperparameter tuning. After hyperparameter tuning, we got R2 score as 96% on training data and 91 on test data. Thus, we improved the model performance by hyperparameter tuning. Thus, gradient boosting regression, the grid search CV and random forest grid search CV gives good R2 score. We can deploy this model. In terms of feature, temperature, and R plays a very important role in following three models. Other feature importance are different in three models. I'm concluding this project. Thank you.